Welcome everyone. So this is our 60th live stream geometry, and we have 3 other people here with us so far. And today I'm going to continue with 4 problems from the Saudi Arabia training for the IMO, and 2 other problems that I chose from the Iranian Geometry Olympiad, which just happened very recently. But if we end up getting through those, which some of them look pretty difficult, then I think I might try 2 more from the Vietnam Math Olympiad that just happened recently. So with that, I'm going to share my screen. And before I do that, if you want to join any future sessions, so if you're interested in joining us, feel free to email me at mgreenb801@gmail.com. It's in the description of the video, and we meet every Sunday at 8 a.m. US Central Time. All right, so let's get started. So actually, I am gonna start with this problem. So this problem looks really interesting. It has a super simple statement, but I'm not sure how easy it really is. So we have a triangle ABC, and O is the circumcenter. All right. So I'll call this O, and then H is the orthocenter. That's H. And then we draw the 9-point circles of AHO, BHO, and CHO. And we want to show that they have 2 common points. So we know that they have 1 common point, right? Because they all pass through the midpoint of OH, but we have to show that they have another common point. So these problems are really hard. I haven't, like, problems that ask you to show 3 circles are coaxial. I haven't found like a general way to solve them, like in general. So let's see what we can do with this problem. So I'm going to do a lot of different midpoints here. And so the circumcircle EGK is the 9-point circle of ABC, but we want to show that this circle, DEF, DGI, and BKI are coaxial. And this reminds me of something from the Discord Geometry Olympiad, kind of, where we had to show like, I think we took the foot of the altitude and then we drew AO and we let it meet the circle, and we had to show that like those three circumcircles were coaxial. So
it was the opposite, actually. You take the AO, which intersects BC, and AH intersects this circumcircle.
Okay, so it was the opposite, and then we had to show those were coaxial.
That problem is really nice and really crazy.
Really difficult, yeah.
I read the solution of it, and it uses 2 inversions and stuff like that. So,
wow, I'll have to keep trying it. I haven't looked at it too much, just because, yeah, I don't have a lot of time these days. But I'll have to look at it sometime because it just seems really interesting. But yeah, I don't know if this problem is that hard or if it's easier. So let's see.
Oh, it looks like that intersection point lies on the 9-point circle of ABC.
Really interesting. So basically, oh, then that might make the problem easier, because GEK is the 9-point circle of ABC. So we really only need to maybe look at one of those 3 circles and then show that there's something about that point that's like unique. So Yeah, for example, what if, oh, whoops. Okay, so that's a 9-point circle. Let me draw the circumcircle DEF. Basically, we want to show that there's something special about this intersection point here, so that it's the same point no matter what circle you take. So that point L, can we show L as the same? Like basically we want to show LGDI as cyclic, and then by symmetry we'd also have LDKJ as cyclic. Is that right? Yeah, we want to show LGDI as cyclic. I don't know if we can do an angle chase. Oh, Khan is joining. All right. Hi, Khan. Thanks for joining us. So Nguyen was saying, did you just take the VMO this weekend?
Yeah, we did.
Yeah, that's right. You told me when you messaged me. So yeah, you're going right straight from that into doing more math.
Yeah.
So yeah, so we just started. So this problem, it looks like it has a simple statement. So you just have a triangle ABC, and O and H are the orthocenter and the circumcenter. And then you take the 9-point circles of AHO, BHO, and CHO, and they all meet at 2 points. So they're like coaxial. That's what we have to prove. But what we found was that the other point that they all pass through, it lies on the 9-point circle. We haven't proven that yet, but that's what it looks like. So all these different circles concur, and they meet on the 9-point circle, but we haven't proven it yet. So. But I like the idea of showing that GLID is cyclic, because we know angle IGD is angle HOB, and so we need to show angle ILD is HOB. So basically ILD, and basically we need to show ILD and IOD have the same size circumcircle. Maybe it's worth trying that. So we want to show GLID is cyclic. And so yeah, I'm trying to see, can we reflect, like what if we reflect O over IB? So that's like point O prime. Basically, we want to show that IG O prime D is cyclic. Yeah, maybe this isn't as bad as hard as I thought. So, sorry. Oh. Yeah. So wait, O prime is just the foot of the altitude of O from, basically we drop a perpendicular from O to BH and we call it, maybe I could call it P instead. And then we just want to show that PGID is cyclic. And then that would solve the problem. In fact, PGID, I think it might just be an isosceles trapezoid.
What do we need to prove? What?
If we can show that DPGI is cyclic, or P is the foot of the altitude from O to B.
That is just the 9-point circle, right?
Yeah, okay. So yeah, I think I've solved this. So okay. So I'll just start out by saying label the midpoints of AH, BH, CH, AO, BO, CO, and OH as shown. Just because I don't feel like writing out all the letters. So then where did I need that. Whoops. And then let the 9-point, we want to let the 9-point circle of ABC meet DEF at a point L. So I'll just say let L be the intersection of the 9-point circles of ABC and AOH. And then we want to show that L is actually also on the 9-point circle of BOH and COH. So so first I'm going to say let P be the foot of the perpendicular from O to BH. Then DPGI is cyclic. So they all lie on the 9-point circle of BOH. And once we know that, then we can do an angle chase to show that L also lies on that circle. Because, wait, now I'm starting to wonder if I actually solved it. So I wanted to show that angle ILD. Oh, yeah, maybe I didn't solve it yet. I wanted to show that angle ILD is IGD. IGD is DOB. Yeah, I need to show L lies on the 9-point. Yeah, I haven't really solved it yet. I don't think. I got confused.
Yeah, it would have looked a bit too easy.
Yeah. I wonder though, it almost looks like maybe DPLI is an isosceles trapezoid. Let's see, DPLI. That almost looks like an isosceles trapezoid. Yeah, let's see. So yeah, maybe we could show that. Can we show LI is parallel to DP? So DI is half of BH. Yeah, PL, I'm not sure how you would show that. So PI is equal to OI, which is, so PI is half the radius of the Circum Circle. Can we show DL is half the radius? So DE is half the radius. So can we show DL is equal to DE? Oops. Sorry. Oh, of course DL. Wait, so D. Oh yeah, because D is the 9-point center. In fact, yeah, so I forgot that. So yeah, DL is equal to DE, which is half the radius of the circle. Actually, just because LI is on the 9-point circle, DL is half the radius. And then PI is also half the radius because what? Oh, because BPO is a right triangle and I is the circumcenter. So PI is equal to IO is equal to IB. Okay. So we know PI equals DL. Now, can we do something else to show that that's an isosceles trapezoid? If we can show that PD is parallel to LI, that would solve the problem. Yeah, looks like there's a couple of ways to go here. Or we could show angle DPI equals angle PDL. So angle DPI, we know it's equal to angle DOB by symmetry. And then, which is angle HOB. And then angle DPL, can we calculate that somehow? We're just missing one thing here. Let me
real
try.
is GLDP as consequently.
If we can prove that, that would solve the problem. Or actually, do we know that? We know that GPID is cyclic. If we can show that L also lies on it, that would solve the problem. So yeah, GPDI is an isosceles trapezoid. So if we can show that PLID is an isosceles trapezoid, then that means that they're all cyclic and they all lie on the same circle. And then that would solve it.
Looks like point L is the Feuerbach point.
Oh, really? Wow.
I kind of thought about it a long time ago, but didn't check it.
Interesting. So the end circle is actually tangent at L. This reminds me a lot of, I don't know if you've read I-3435. He was previously on this channel, but he has, he wrote like a book and there's like something called the Poncelet Point. Kind of reminds me a little of that.
Oh, I think that is not actually true.
Oh, it's not the Feuerbach point?
No.
Okay. That would have been really cool. So PI equals DL, we know that.
Can we somehow prove that PL is equal to half of HB? HB.
HB.
Yeah, then it will be equal to DI, and then we have the PDIL is an isosceles trapezoid.
Yeah, no, that's a good point.
But I think it's a little hard to calculate PL.
Yeah. I'm not sure how to do it. Maybe there's some congruent triangles somewhere. So PL, we want to show it's half of BH. Can we show let me check point L. Is there anything else that's special about it? I don't think BL and B are collinear, because then no. Yeah, I like trying to show that LI is parallel to PB. But yeah, I'm not totally sure where to start with that. Maybe we could calculate angle GLI. What if So yeah, PI equals DL. So what does that mean? If LI is parallel to PD, how do we are there any special points? What if I reflect B over L? Then that means we want to show OB prime is parallel to BD. That kind of made things messier. Let me check if okay, let me move it back to the way it was before. Well, maybe we could show PDL is congruent to DOI somehow. Or GID. Well, yeah, actually, so I think we want to use something more about L. So like if we reflect, let me check the chat. Yeah, that's true. If the centers of the circles lie on a line, that does solve it. Yeah, because yeah, we know they all pass through point B, which is the 9-point center. We want to show that all three of them also pass through L.
Maybe we should invert.
All right.
I think that.
Yeah, I think if angle chasing isn't working, we should change to using inversion.
Okay.
Yeah, I think that inversion around the 9-point circle of ABC looks fine.
Okay. So we invert with the center D.
Yeah. Since all those circles would become lines, and we for every circle we practically invert just 1 point, I think.
Okay. So all those circles would become lines because they all pass through D. And then E, L, and K would stay where they are. an F. Let's see, where would F go? Let me try reflect about circle. Oops, sorry, that's the wrong point. I want to reflect J and I. Okay, so we want to show that EF prime, basically, yeah, I think that's a really good idea. Yeah, we want to show that EF prime and then, sorry, I'm confused. Does that really pass through L? Huh, interesting. Okay, so we want to show EF.
Of course, it passes through L because of the inversion. Right?
Okay. Yeah, it has to. You're right.
We have to prove that all those three lines concur at L after inversion.
Oh, okay. Oh, okay. KJ prime and GI prime. So yeah, we have to show that those three concur at a point. So is there anything about F prime? Let's see. So DF and F prime are collinear. And DF is half of AH. So we have DF times DF prime is half the radius of the circle. So basically AH or squared. So AH times F prime D is going to be the radius squared. Interesting. Thanks for joining, Sergio. So AH, it's twice the distance from O to BC. So yeah, maybe this is like something with similar triangles. Let's see. Let me delete these for a sec, or hide them. Yeah, what can we say about F prime, I prime, and J prime? I wonder, so DF prime times AH is the radius squared. Which is, yeah, OA squared. So yeah, we have to find, I'd like to find something else special about f prime. Yeah, maybe we could even use Desargues theorem or something. But first, what can we say about f?
I have an idea of using pole and polar, but I haven't tried it out yet.
Okay, yeah, see if you
So
can.
you can see that f and f primes are, because they are inverted about circle D. So f prime must lie on the polar of f.
Mm-hmm.
So can you draw the polar of f, like the
Yeah.
line polar of f prime? I mean,
Yeah, hold on one sec. So here's the polar of f.
f prime, f prime,
Okay.
f prime. And so can you let it meet the tangent at E of the circle D? No, I mean, can you draw the tangent at E of circle D?
Like here and here, the tangents.
No, I mean the tangent line at E
Oh,
of
at
the
E.
9-point circle.
Yeah.
And so we need to prove that f prime, excuse me, what did we need to prove that they are concurrent? Which lines that we need to prove that they are concurrent?
These or oh, we have to show f prime E.
And so yeah, can you label the intersection that of the two lines?
So this point right here.
Yeah, it lies on the circle too.
Okay.
So that is the polar of that's the pole of EF prime.
Okay.
So somehow we can prove that that point and the two other similar points that is collinear. Then we can show that F prime E and the other two are concurrent.
Okay. So M is the polar. M is the pole of EF. For EF prime. So just trying to think about this. So we have EF prime, then we have JK prime. So like if we drew the pole, boy, that's weird.
So basically, M is the pole of F prime E. So if we can prove M and the other two are collinear, then we have the three lines are concurrent. So that's basically what we need to prove.
If we can prove what's collinear?
You can just determine the two similar points of like how I did with M.
Okay.
Like connecting. Furthermore, M is also the auto center of AEF.
Okay. So basically draw the tangents at points K and G. So we have all those tangents.
I have another reasoning why that would work.
Okay.
Like because M is the antipode of D, and we want to. It is equivalent to show that the centers of those 9-point circles align on a line. So that is equivalent to like doing a homotopy with factor 2 at D.
Okay, I see what you're saying. Yeah, because instead of showing those three centers line a line, we're showing the antipodes. We're just doing a homotopy with ratio 2. Okay, so That's interesting. Do we think this is, so yeah, I'm not sure if this makes the problem easier than what we were doing before, but yeah, I don't know. But it's kind of interesting because it looks like these concur. So maybe that tells us something. So yeah, J prime K, not only does it pass through L, but it looks like these concur right here. So maybe we could let ID intersect the circle at N. And then we want to show L. Yeah, I think that might actually help a lot. Sorry, I'm going to hide a couple things here. I'm not. Yeah, let me hide the stuff with the inversion just for a second. What if we let ID intersect the circle DEF at point N, and then we want to show that L, N, and K are collinear. I think that would solve it, because I think we could then use an angle chase. Okay, so we want to show L, N, and K are collinear. It almost looks like the Gauss line in a way. Like, yeah, that's not something I expected, that L, N, and K are collinear. Sorry. N lies on AH. Ah, I think you might be right. No, I think it's a little bit off. Let me move. Yeah, not necessarily. So K is the midpoint of CH, and yeah, how would we show that? So K and L both lie on the circle itself, right? So basically we want to calculate the angle between KL and ID. And we want to use that L lies on DEF. So yeah, that's the thing. We've never really used that L lies on the Circum Circle DEF. We have to use that somehow. That means angle FLD is FED. So FLD is equal to angle FAH. No, I'm sorry. Is that right? It's AOH. So FLD is AOH. So I wonder, is triangle FLD half the size of AOH? Is FLD just half of AOH? I think it might be. Because FD is half of AH, DL, yeah, DL is half of AO. Or wait. So actually, if we draw this point right here, FDRO is a parallelogram, right? So FLD is equal to FOD. Yeah, I'm trying to use information about L. We know that FLD is FOD. Which is AOH.
I think that I can prove LNK collinear. I'm not sure.
Oh, really? How do you prove it?
Can you draw the segment ER?
Yes.
We have we need to prove that angle LNI is equal to angle KNR, right?
LNI is KND, right?
Sorry, KND, yeah. First we have LNI is equal to LED.
LED. Mm-hmm.
Equal to LER.
Yes.
Equal to LKR.
Yes.
And we have hold up. KR is parallel to DI.
Yeah, because KR is parallel to BH and DI is parallel to BH. Oh, that's perfect. Yeah. So yeah, I think this might solve it. So let me write that out. So let DI intersect the circle DEF.
Wait. I think he proved that LNI is equal to LKR. But how do we prove that LKR is equal to DNK?
Oh, I have mistake. Yeah.
Because
Sorry,
LNK is in collinear, so NKR cannot, I mean, DNK cannot be equal to LKR yet, because they are not
Sorry.
collinear.
Sorry.
Wait, so that doesn't work? Because I thought we showed that LNI is equal to LKR, and then DI is parallel to KR, right? I thought that worked. Let me try it. So angle LEI is equal to angle, I'm sorry, LNI is LED. Is equal to angle LER. Which is equal to angle LKR. And then we have KR is parallel to BH, which is parallel to BI. Is that right? BH and BI, sorry. And so that means that LN and K are collinear, right? Oh, whoops. I wrote all that there. Sorry. There we go. So actually, let me define N. So and then once we know that, yeah, okay, angle chase looks okay. So we wanted to show that IL is parallel to DP. So what was my idea here? So Stefan, what's your idea using the angle chase?
No, I just commented on this angle chase.
Okay. What was I thinking? Got. So then, yeah. I feel like N. Oh, J prime was also on this. That's what we realized. So but I think this idea still probably.
Do we know that J prime is on that line?
No.
Oh,
but we just noticed it.
okay. Okay.
So yeah, we want to show PD is parallel to LI. We know angle IL, we can find angle ILK. Basically, we want to find what's the angle that PD makes with LK. I think we're really close.
Sorry, do you try to solve this problem by using inversion or just angle chasing?
Yeah, we tried inversion before. So if we can show that, like if you invert J about D, if we can show that lies on LK, that would solve the problem.
Oh, I got that.
Oh, you know how to do that?
Sorry, sir. Just I just said that I got what you need to do.
Or what? Let me try something here. So we could also use that KG is parallel to BC, right? We've never used that. So what if we try to show that angle DPL plus angle PLI is 180? So DPL is the same as DPO plus, let me think about this. So we can calculate PLI is PLK plus KLI. Is LIN isosceles? No. All right, you guys want to move on to the next problem and finish this later?
Yeah, let's
Yeah.
move on.
Okay. So this is also an interesting one. So you have the triangle ABC, and D is the point of tangent C. Of the end circle. And then we draw the end centers of ABD and ACD. I'm going to draw that in center 2. And then we draw the, so yeah, I'll call it JB and JC. Let me call this I. So we want to draw the circumcenter of A, JB, JC. And we want to show that lies on AI, basically. Why didn't the name of this change? I. There we go. So we can call that G. One second, guys. I'll be right back. Sorry. All right, thanks everyone for waiting. I'm back. It looks, those end circles, I don't think the end circles are tangent, are they? Is that really true? I would be very surprised, but maybe you're right. What if we zoom in a bunch? It does look like they're tangent. I did not expect that. What if we make this like an obtuse triangle? Then it would probably, yeah, it almost looks like, oh, can we prove that they're tangent just kind of by a length chase? Because if we let this be tangent at a point X and we let this be tangent at a point Y, then we could show AX equals AY. Because yeah, we want,
you can, because there's a formula to calculate the length of that segment.
Yeah, basically we want to.
Yeah, can you just name the point? The
point of tangency, yeah. But yeah, I think they are. I think it's not hard to show that they're tangent.
Yeah, so we can calculate AH. It is equal to AB plus AD minus BD R over 2.
Okay.
Yeah, and similarly
Mm-hmm.
to H prime, which is the tangent point of F, the circle F.
Yeah.
Yeah, I think we can prove that.
So yeah, AH is AB plus AD minus BD over 2. And then for the other, let's say AH prime would be AB plus AC minus CD over 2. And then it's easy to calculate that those would have to be equal because, yeah, because BD is, yeah. So yeah, they're
We can
tangent.
calculate that, yeah.
Yeah. Okay, so we want to show that AD and AI are isogonal. Oh wait, how did the name of these circles change back? Whoops. JB and JC. Oops. The diagram disappears so easy. So I might as well draw this segment and this segment. Okay, so we want to show AD and AI are isogonal. So yeah, we know angle JAB is half of angle BAB. Oh, it's probably pretty easy, I think. We just, because JBAD is half of angle BAB, and angle, oh, we need JCAG, but JCAI, that's CAI minus CAJC. Yeah, no, it's just an angle chase, really. So I think it's not too hard. Yeah. So I'll say let the in circles of ABD and ACD be tangent to AD at H and H prime. So then we have so AH is equal to AB plus AD minus BD over 2, and also AH prime is equal to AC plus AD minus CD over 2. And also, we know BD and CD, so, or we know that BD is AB plus BC minus AC over 2. And we know that CD is AC plus BC minus AB over 2. So combining all that, H equals H prime. Okay. So then JB, H, and JC are collinear. Now the angle chase isn't hard because so I'll just start out saying I'll just call this O. Why not? So let O be the circumcenter of A, J, B, J, C. And then AO and AH are isogonal. That's kind of well known. And so then basically angle JCA O, we want to show as angle JCAI, but JCAO is JBAH, which is half of BAD. So yeah, I'm just going to type them all out right now. So angle JCAO is equal to angle JBAH, which is equal to half of angle BAD. And then we could do the same with JCAI. Well, so it's an angle, so it's a calculation. So angle JCAI is equal to angle CAI minus angle CAJC. And CAI is half of BAC, and CAJ is half of CAD. So then that solves it. So that's half of angle BAC minus half angle CAI, which is half of angle BAD. Which is angle JCAO. So that means that AO and I are collinear, which solves the problem. Okay. the circumcenter. Yeah, that was not that hard once you find the right ideas. So I'm going to move on to the next one. Okay. Yeah. Let's see. This one looks